Okay, so before we went to break, we learned the conditional probability rule, right? Which was A given B equals the probability of the intersection over B, over the given. So remember that said the probability of A happening given B equals the intersection of the two over the probability of the given. You guys, if you wrote it the other way, like this, the numerator is always the same. It's the denominator that changes. So I'm giving you this rule, but it really doesn't mean anything until we can apply it, okay? So we had done a little bit with two-way tables before break, so we're going to do this one now, okay? So here is this table. A recent survey asked 100 randomly selected adult Americans if they thought that women should be allowed to go into combat situations. Here are the results. So 32 men said yes, 18 said no. 8 females said yes, 42 females said no. So how many men were there? 50. How many females?
50.
Okay, which that should be 100, right? How many people said yes?
40.
And how many said no?
60.
Okay. So we're going to need those numbers, okay, because those are going to probably be a given. So if you get a two-way table, always find those marginal distributions, okay? And right now we're just going to use them in counts. We're not going to use them as percents because we just need counts. So it says find the probability of a yes answer given the person was a female. So it is the probability of yes given that they were a female. Now, we could have turned this around, you guys. We could say, find the probability of a female answer given the person said yes, okay? So, the numerator is where they intersect. So, where is the intersection of yes and female? How many said yes and female? 8. Out of how many females?
50.
I wrote it like that. You can reduce it, and I also have this answer. I don't think it would matter if you wrote either answer, but I always start off with the fraction. So you always want to make sure that the fraction is written, okay? Okay. Now the next one says what? Find the probability that the respondent was a male given the response was a no. So this time gender comes first. And it was given that they said no. So again, it's the intersection in the numerator. So how many males said no? 18 out of how many no answers?
60. So no answers.
And I believe it's 0.3 when you did it. Yep, okay. Good so far? So that's a conditional, okay? Now, I wish that I could tell you that every time they give you a conditional probability, that they always say given, right? That word given is there. It's not always there. So tomorrow what I want to do is I'm going to find questions that are like this, but don't give the word given. And we're going to talk about how we know which one was the given, okay? Now we're going to toss 2 balanced coins. That means, you guys, they're fair. Do you understand that they weigh the same out? And we're gonna let A equal the head on the first toss and so event A is the head is on the first toss. Event B is the both tosses have the same outcome. Are events A and B independent? Explain your reasoning clearly. Okay, so how do we prove two things independent? This is a little bit what we did before break. The intersection of the two, right, equal the probability of A times the probability of B, correct? Do you remember that? And you guys can't see that. There you go. Okay, so let's think about event A. And what is the sample space of event A? You get a head on the first toss. So what would your outcomes be? You flip 2 coins. What would your outcomes be, Amy?
Heads and tails.
So if you're flipping 2 coins, so it would be, you either get head, head, right? Or you would get head, tails. What is the probability of event B? All right, not the probability. What's sample space? We'll talk about probability in a second. Oh my goodness.
Tails, tails.
What is it?
Head, head, tails, tails.
Head, heads, oops. Head, head, tails, tails. Now let's think of the entire sample space. So if you flip 2 coins, right? What are your possible outcomes? Head, head, right? Head, tails. What's your next one? Tails, what? Head. And then tail, tail. Right? Because if you're flipping 2 coins. Okay, so now that leads me to the probability of A. What is the probability of event A happening? What is it? 50% or 1/2? The reason I'm not going to do it in percents is because of the probability rule, okay? What is the probability of B? Okay. And what is the probability of the intersection of AB?
25.
Because it's 1/4, right?
Yes.
So does 1/2 times 1/2 equal 1/4?
Yes, it does.
So are these events independent?
Yes.
And you should probably write a sentence that says, explain your reason clearly. Yes. Are events A and B independent? Yes. Events A and B are independent. Did I explain my reasoning? Can they clearly understand what I did? I showed work. I showed everything. Yes. So there should be a sentence that says, yes, A and B are independent. Okay. Here's this next one. Parking for students at Central High School is very limited, and those who arrive late have to park illegally. Did we already do this one?
No.
Okay. And take their chances at getting a ticket. So they park illegally and they're taking their chances to get a ticket. Joey has determined that the probability that he has to park illegally and that he gets a parking ticket is 0.07. So he parks illegally and gets a ticket, okay? He recorded data last year and found that because of his perpetual tardiness, the probability that he will have to park illegally is 0.25. So he knows he's going to be tardy. He's going to have to park illegally. Suppose that Joey arrived late once again this morning and had to park in a no parking zone. Can you find the probability that Joey will get a parking ticket? If so, do it. If you need additional information to find the probability, explain what is needed. Well, there really isn't. Okay, so. Did I spell that wrong? You know where I'm going. Nope, didn't. Yay. Can you find the probability that Joey will get a parking ticket? So, what is it? He gets a parking ticket if he what? Parks illegally. Okay, so we know that the intersection, right? So the intersection of parking illegally and getting a ticket over parking illegally. So we learned that. So what's the intersection of gets a ticket and parks illegally? 0.07. And what's the probability if he parked illegally? Now, you guys, because it's a decimal over a decimal, you're not going to leave it like that, right? Like you have to actually divide it out and give them an answer. So, what is the probability that Joey gets a ticket? What is it?
0.49. Oh wait, no, I'm done. 0.28.
Yep, there you go. Now, I know that some of you are looking at that and you're like, well, I wouldn't have done it that way. I didn't know. You guys, if you start thinking and you start reading these, right? You're like, okay, why did they give me 0.07? Why did they give me 0.25? What do I need to know? Well, okay, I know that's the intersection and I know he parked illegally. So what do I know about the intersection and this? Oh, it's a conditional probability. Okay, this is one of those ones where they didn't use the word give, but you can see like why did they, so you always have to ask yourself when you see a problem like this, what did they give me and what can I do with what they gave me? Very rarely are they going to give you something where you need additional information. If that's the case, like if you're talking like a free response question on the exam, you guys, and you're like, something's missing, then read the rest of the questions, because the nice thing about AP Stats is usually what happens is they give you this question, right? And they say something's missing, and then the next question is, it has to do with the part A. So that's the good thing about it. So read the entire thing and read about what they want you to find when you go to answer the question. Okay, we got one more question on this particular quiz, and then we'll go to 6.3b. Two cards are dealt, one after the other, from a shuffled 52 card deck. Why is it wrong to say that the probability of getting two red cards is 1/2 times 1/2 equals 1/4? What is the correct probability of this event? So why is it wrong to say that?
Because after you pull the first card, it becomes 51.
Right, because you didn't replace the card. So that's the first thing. Why is it wrong to the probability of getting two cards? Because you never replaced the first card you drew. That's the first problem, okay? And then what is the correct probability of this event? So let's talk about that. How many red cards are there in the first time? Anybody know? 26 out of how many red cards altogether? 52. So that's the probability of drawing a red card. Normally that would be fine, especially if you put the red card back in, right? Well, it doesn't. Yeah, you put the card back in. Well, you didn't put the card back in, and you're assuming that the one that you picked was red. So now David has already said that how many cards are left? 51, because we took a card out. But we also assumed that we took out a red card. So if there was 26 red cards to begin with, and we took one out, how many do we have left?
25.
It's close to what they thought though, right? It's not horrible, but it's not exactly a quarter. Now, you guys, I said out loud, why is it wrong to say that the probability of the cards is this? I didn't write it, so you should actually write it because we did not replace the card that we took. That's why it's wrong to say that. It's because there was no replacement. So we had talked a little bit about that before break, is that you really need to know if the problem is asking you to replace what you took out or not. Because if it doesn't, if you do not replace it, now it's not a independent event anymore. It's a dependent event because it's depending on what happened the first time. Okay?